Good morning, everybody. I'm glad to see that you all came back after the first episode. So hopefully you got a good night's sleep and your brains are well rested, because I'm sure we're going to get a lot more to think about from Lawrence here in a moment. And with that, I'm just going to turn it over to you.
Good.
And we'll get started.
Let's start, because I don't know how long I'm going to go. Thank you. Oh, there, you don't know. It's not always, it is surprising to see people are back. So I'm really happy about that. This one, I think, will be, well, I don't know, it's going to be more fun, but it's going to be all over the place. It's going to be really simple. As I say, we're going to do time, space, quantum mechanics, particle physics, and consciousness. Okay. But I want to set this up for Jim's talks, and in some sense, I want to talk about the world as an illusion. And science has really told us the world is an illusion, but it's not the kind of illusion that sort of New Age people would argue it is, because we've learned about it, and in particular, we can predict what's happening, and the illusion. That's the wonderful thing about science, is it's told us that what we think of as common sense and normal is not always normal. And it's, to me, that really is one of the values of science, as we talked earlier about what science is good for, and why I think it's nice for kids to learn it. Because it's really, I tell students, I used to tell students, that the one thing I hope for them when they go to college is that something that they profoundly believe in with their heart and soul, which makes them, which is central to their being, should be, I hope that they experience that being proved wrong at some point in there, because that's what the liberation that science provides. The idea that things that we think are sensible are not, and it teaches us we have to expand our minds to realize that, you know, that our myopic view of reality is just that. It's a myopic view of reality. And this is one of my favorite quotes. Actually, it was a friend of mine, Werner Herzog, who gave me this quote. It's a great book to read, The Peregrine. It's about a guy who follows a peregrine falcon basically for 6 months and just becomes the falcon. It's a wonderful book. One of the nicest nature books I've read. But anyway, the hardest thing to see is what is really there, and that's what I want to talk about in many different ways. What's really there is just so much more than what's on the surface. And I'm going to give you a bunch of examples. Some of them is to teach Jeff some things we were talking about, and we'll see if that works. Okay. Our myopic view of reality, I like to think of this. Those of you who live in California here, these are ice crystals. Okay. You may not have seen them on your window, but I certainly do. And, you know, from outside it looks beautiful, right? But what I want you to think about, and we'll do this throughout the talk, is I want to think about what it would be like to live on one of these ice crystals, okay? The world would look very different. You know, they're pointing in all sorts of directions here. But if you lived on one, there'd be something very special about the direction along the crystal. The laws of nature would be different along that direction than all the other directions. Because, you know, you're in a very particular configuration. There's more stuff here than perpendicular. And so if you were a physicist living in that crystal, or just a normal person, you'd just take it for granted that the one direction was special in nature. Okay? But that's myopic. That's just an example, an accident of your circumstances. And I'm big on accidents of circumstances, because I think that's what life is, largely, an accident of circumstances. And so take that picture and keep it in your mind, because we are constantly going to be reminded that we're living on an ice crystal, that what the reality is just deeper, and the accident that we see is just a product of our circumstances. Okay? So we'll start. This is one of my favorite stories, and it's philosophy. That's why I threw it in there. You know who this is? You do, man. Yeah, you know, it's Plato. And I did used to read philosophy when I was younger, and I did like the Republic. One of my favorite stories in the Republic is the parable of the cave, and Plato likened our view of reality to being in a cave. This was from my high school textbook. I found it, so it's old, really old. So that we're people that are sort of chained to see the back of the cave, and all of our views of reality. There's a fire behind us, and it projects shadows of reality. Reality's here, but these people can never see it. They can only see the shadows of reality. You notice that it was 1950s, that these people are tied up are women in bikinis, which I kind of found interesting at the time. In Plato's time, it would have been little boys, but that's a whole different thing. So people see that, and he said the job of a philosopher, because they didn't have physicists then, was to try and interpret these shadows and try and interpret the reality. And that's really what we do. That's the job of natural philosophers and scientists, is to take the shadows, which is what we're seeing, and interpret it. I'll give you an example. So I think I have this example here. We'll see. I forget if I put it. So here's an example of what they might see. They'd see a ruler, the shadow of a ruler, plastic ruler on the wall. And sometimes during the day, it'd be that big, and other times it'd be that big. So they would say, well, length changes throughout the day, depending upon where you are. And the philosopher, however, would look at that and say, no, maybe there's another dimension. It's not all two-dimensional. And maybe the length is really a constant. It's always the same, but we're just seeing different projections of it. So, if my arm is the ruler, okay, and if you could do this with one eye, it doesn't matter. It's probably easier. You don't have depth perception. It's that long. But if I rotate the ruler, and you're looking at the projection of the ruler on the screen, the shadow will get smaller. So the philosopher would say, what's really happening is there's an object that has a constant size, and there's another dimension in nature, and it's just rotating. And so he would, or she, would then determine this underlying reality, a constant of nature being length. Although the people in the cave would have always thought, no, length is just something that changes during the day, and it's not constant. So that's the kind of picture that you might have happened, and that's exactly the first example that I want to give you. So this is the image of it. As you take the ruler and you rotate it, the shadow projects is smaller on the screen. Okay, we all okay with that? Okay. This is not a very good blow-up of one of my favorite physicists. Anyone know who this is? Probably not. Michael Faraday. He was the greatest experimental physicist of the 19th century. And I like him a lot. He was self-trained, didn't go to school. In fact, what he did was he was a printer's apprentice. And he attended the lectures of the head of the Royal Institution, a guy named Humphrey Davy, who was a very famous chemist. And he attended the lectures, and he took beautiful notes, and he bound them together in a book, which he presented to Humphrey Davy. And then Davies asked him to be his assistant. And that's a valuable lesson for students, which is always to suck up to your instructors. And I try and tell students that, but no one's ever given me a bound volume. But Faraday is responsible for basically everything that's happening today in this room. He discovered the experimental laws that he discovered were the laws of electromagnetism. In fact, he had a laboratory, speaking of utility, he had a laboratory that had all sorts of neat stuff in it, jumping frogs and all this stuff. And there's two apocryphal stories, I'm not sure either is right, of someone talked about Queen Victoria coming into his lab and saying, what use is all this? And he said, what use is a newborn baby? But I like the other one better. So it says that Benjamin Disraeli, the prime minister, came in and said, what use is all this? And he said, this is so useful, one day you'll tax us for it. And of course he did, because he discovered what is essentially electrical power. Power is that lights and the computer and everything else, and we do get taxed for it. But what I like about him, he wasn't trained mathematically, so he thought pictorially. And he tried to imagine this picture, which actually Newton never didn't really get. Electric charges repel each other. Two like charges repel each other. Remember that from high school or whatever. You take two electrons and they repel. The electric force repels. And the question is, how does this charge know to be repelled by this charge? Okay. And Newton actually thought in the context of gravity, and he just said, I'm not going to frame any hypotheses. It just works. The Earth is attracted to the sun. I don't know how. And Faraday said, well, I'm going to imagine just a picture that helps me. I'm going to imagine that if I have a charge here, that there are lines radiating out in space. I'll call them field lines. And the bigger the charge, the more lines. Okay? And then I'm going to imagine if I put a charge here, it sees that field right there, and it knows to be repelled in the direction of the field lines. So it was his sort of heuristic way of trying to picture. And it turns out the mathematics is exactly right, because if you really want to work it out, that if you draw a circle here, the density of lines falls off as one of the area of the circle. but the strength of an electric field falls off as 1 over the square of the distance from an object. So it gives you exactly the right mathematics. It's just a picture, and it was just a crutch. He invented it as a crutch. I mean, these things weren't real, or so he thought. And you get lots of neat stuff. You put two of them together, and the field lines can't cross. You get all sorts of neat pictures. And this reproduces exactly the algebra, the mathematics. And it was wonderful because he invented this crutch, which was not real. Okay, but it was an essential piece of his thinking. Now, what he discovered, it had been well known that that if you move a charge, if you have a current, it creates a magnetic field. You know, that's what an electromagnet is. Current flows through and it has a magnetic field. You've maybe played with those. So people knew that electric currents produced a magnetic field, but the idea is, well, could a magnetic field produce a current? Does it work the other way? And people tried and tried and tried. And Faraday tried in his laboratory and couldn't get it to work. Till one day, by accident, so he had a little wire set up, and he had a magnet, and he put it next to it, and he couldn't get a current to go in this wire. And the magnet he set was an electromagnet. So when you turned it on, a current flowed, and you caused a magnet here. And what he noticed was when he turned the current on, and a magnetic field was suddenly created, suddenly then a current flowed in that other wire. We turned it off, suddenly a current flowed in that other wire. So what he discovered was that if you change the magnetic field in a region, you'll produce a current. So a changing magnetic field produces a current. What causes a current to flow? Well, a current to flow is some electric force. So he could think of it, and this is what this guy, the greatest theoretical physicist of the 19th century, James Clerk Maxwell, another one of my heroes. He died before, well, he died, all of you are older than he was when he died, and but he nevertheless changed the law. He produced what is now called Maxwell's equations, the laws of electromagnetism and physics. Nerdy physics students wear them on their T-shirt, 4 equations of Maxwell's equations. With it underneath it says, "Let there be light," because what he said was, I'm going to codify what Faraday had discovered. And I'm going to say, well, we know that a changing electric field, namely a charge moving, will produce a magnetic field. And what Faraday just discovered is that a changing magnetic field will produce an electric field. He's suddenly talking about fields, this crutch, this invention that Faraday had developed for his own mind. But they weren't real. But Maxwell basically said, well, maybe they're real. And in fact, if they're real, I can imagine doing something. I can imagine taking a charge and shaking it. What will happen? Well, it moves. It starts to move, creates a magnetic field, but as it starts to move, it creates a changing magnetic field. So this charge is here, produces a magnetic field, but the changing magnetic field that is here will now produce an electric field. But the electric field is changing, so that'll produce a magnetic field. And the magnetic field is changing, and that'll produce an electric field. And so if I shake a charge, I might produce a disturbance that goes throughout space. That looks like this. And he used the and it's a wonderful calculation. You can do it in, well, probably first or second year physics. It turns out from the fundamental laws of electromagnetism, you could measure the strength of the forces between two charges in a laboratory. You can measure the strength of the force between two magnets in a laboratory. Those are two fundamental constants of nature. Plugging them in, he said, from those two fundamental constants of nature, I can calculate the speed at which that disturbance will travel. And he calculated it, and guess what he found? He found that that speed was the speed of light. And he said, maybe light is an electromagnetic disturbance. And that's, of course, exactly right. So that was just one of the most beautiful calculations in 19th century physics. And as I say, it's wonderful to be able to do for undergraduates. So Faraday and leads to Maxwell, and Maxwell tells us not only are those fields real, but they're as real as they can be because it's light. When I see that light, it's electromagnetic fields that are coming into my eye and that are changing. So fields are as real as you can imagine. You can actually see them, in a sense. Okay? Great. So that was the situation in the late 1800s. And then there was a young guy who was fortunate enough to be born around the time this was discovered. He wouldn't have been who he was if he had been born 50 years earlier. He was another fortunate accident. Okay? You may not have recognized the other two pictures. You recognize this one. Okay? Albert Einstein. And Albert Einstein, to his credit, started thinking when he was 16 or 17. The first, he did a thought experiment in his mind. He said, well, what would the world look like if I were riding on a light wave? The kind of thing a standard 16-year-old thinks about. And what he realized, and people think, we teach it wrong in physics classes. We teach this weird thing about the speed of light being constant and blah, 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 blah. And it sounds like it's an edict, like the Ten Commandments or something that's just written down. And we all buy it as if it's somehow supposed to be. But Einstein was driven to his theory kicking and screaming because what he realized were that two fundamental theories of physics that had been tested. They were the basis of modern physics. Maxwell's equations and something that Galileo had discovered 300 years earlier were inconsistent. What Galileo had discovered, the basis of all of modern physics, is a really interesting fact, that the laws of physics are the same for an object that's moving at a uniform speed as they are for something standing still. In fact, there's no way you can show that you're moving or standing still. I mean, you might have had, especially if in Europe where the trains are smoother, but maybe in a subway station. Have you ever been there and you're on the subway car or the train car and you see the crane next to you and it starts to move, and for a second you don't know whether you're moving or it's moving until you feel the motion, okay? And if there was no motion, you would never be able to prove whether you were moving or they were moving. You would know that relative to you, that train is moving, but that train could be standing still and you could be moving, or the other way around. And you could try any experiment you can imagine to throw a ball up in the air and it comes right back down. Okay? So it feels like you're standing still. In fact, you think you're standing still right now, right? We do. But we're traveling around the sun right now at 30 kilometers per second. 30 kilometers per second, 20 miles per second. We're moving fast, but we certainly feel like we're standing still. So Galileo's fundamental supposition that the laws of physics don't allow you to know whether you're moving or not as long as you're moving at a constant velocity. They're the same for all observers. And Maxwell said the speed of light, if I jiggle a charge, I'll produce a light ray that will go out, and the speed of that light ray is determined just by two fundamental constants of nature, the strength of electricity and the strength of magnetism. I'm going to teach you something they never do in undergraduate physics, but you're going to remember it. They're inconsistent. Why are they inconsistent? Well, when I first thought about how to explain this, my daughter was very young. So the example I came up with had to do with projectile vomit. And so I used to drive her to nursery school. So imagine the following. So my daughter's in the car, in the back seat. I'm traveling 20 miles an hour, which never happens, but let's say I'm traveling 20 miles an hour. And someone on the street watches me, and she projectile vomits in the back seat, hits me in the back of the head, okay? And the vomit is going at 10 miles an hour in the car. Okay, goes from the back seat to the front at 10 miles an hour. But the car is moving at 20 miles an hour. So someone on the ground sees the vomit moving with respect to them at 20 plus 10, 30 miles per hour. We okay? We're all okay with this, the complicated mathematics? Okay, great. But now let's say my daughter is a 21st century kid and has a laser. Okay? And she shines the laser, okay, up the back of my head. What happens? Well, the laser is going at the speed of light. The car is traveling. So a person on the ground, you'd think, would see the laser travel at the speed of light plus 30 miles per hour. Wrong. Why is it wrong? Because Einstein said, look, that isn't right. Because if you saw the speed of, remember, if I produce an electromagnetic wave, it travels at a speed determined by two fundamental constants of nature, the strength of electricity and the strength of magnetism. If the person on the ground sees the light ray traveling at a different speed relative to them than someone does in the car, then for someone in the car, the fundamental constants of nature must be different than they are for someone on the ground. Because remember, the speed of light is just determined by two fundamental constants of nature. But Galileo over here said that's not allowed. There's no way you can do an experiment in the car that tells you you're moving. And so there's no way you would measure in the car that the fundamental constants of nature are different than they are on the ground, because if that was the case, you'd know you're moving. So Einstein said it's inconsistent. Maxwell's theory and Einstein's and Galileo's are just, they don't work. They're inconsistent with each other. A lesser person would have maybe thrown up their hands, but he was creative enough to be willing to throw out one fundamental illusion about nature. He said, well, what is speed? Speed is distance traveled divided by the time it takes to get there. Okay, I came from San Diego. It took me an hour and 15 minutes. I was traveling at 75 miles an hour and blah, 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 on average. And so, you know, if you're traveling at 75 miles an hour and you're 2 hours, you go 150 miles, okay? Speed is distance divided by time, okay? Well, what would I have to do so that the speed that I measure the light ray, if I'm in the car, is the same as the speed that if I'm standing on the ground watching the light ray, not the speed of light plus 30 miles per hour? Well, the only way to make that work is that my measurements of distance and time on the ground must be different than my measurements of distance and time in the car. That'll make it work. Because if we differ, because then we can come up with exactly the same number, the speed of light. It's just that I measure distances and times differently than you. That's insane. Because we all are used to time being the same and distance being the same. But he said the only way to make those two things consistent is to potentially give up that common sense notion that time is universal and space is universal. Maybe they're relative. Maybe they depend on your state of motion. And if I'm moving with respect to you, maybe I measure things differently than you. And in fact, that one of the consequences of that was that there's three consequences. If I'm moving with respect to you very fast, a ruler, say 6 inches long, if I'm moving very fast with respect to you, for you, the ruler will look like it's 4 inches long, or 3 inches, depending upon how fast I'm moving. And it's not like it will just be an illusion. For you, the ruler will be. Every experiment you could do on that ruler would show it's 3 inches long for you. Every experiment I could do in my laboratory moving with me would show it's 6 inches. We're both right. We both just have different senses of distance. Same with time. Timilton 80 changes. Namely, if lightning strikes at either end of this room at exactly the same time, fine for us. But if I'm in a car zooming through here very fast, close to the speed of light, I will see one of the lightning bolts hit before the other. And if I'm traveling in that direction, I'll see this one hit before that one. So for distant events, before and after are relative. Really weird. And time dilates. If I'm traveling very fast with respect to you, my clock slows down with respect to yours. I'm traveling very fast. I see an hour. You see my, well, if you see an hour, you'll look at my watch, I'll see it as being 5 seconds. Time is relative. These crazy implications for which there was no experimental evidence at the time, but he said this is what's required. He just plugged through the mathematics. If we make that supposition that I said, that Galileo and Maxwell, both well-tested theories, they're inconsistent. The only way to make them consistent is this crazy idea that you give up common sense. Okay? Now, I prepared your minds for this because you've seen this image before. Because Einstein's professor of mathematics, a guy named Hermann Minkowski, realized that all of this could be understood if we just said that maybe there are 4 dimensions in nature, not 3. Maybe time and space are tied together in a different kind of 4-dimensional space. And maybe the reason you see lengths contract is because length and time are kind of interchangeable. So that for 2 events, either end of the ruler, they're closer in space, but they're spread out in time now. And so maybe there's a 4-dimensional length that's constant. And in fact, that's the case. You can show that there's a combination of the time differences between 2 events and the space differences between 2 events. For all observers, it's exactly the same. The space can change and the time can change, but all observers will agree that the space-time interval between those 2 events is the same. In a 4-dimensional space, we call it Minkowski space. And I think in 1908, Minkowski said, henceforth, space by itself and time by itself are doomed to fade away into mere shadows. And only a kind of union of the two will preserve an independent reality. So what Einstein had really discovered was that we live in a 4-dimensional space, and that our notions of time are really, and instant and simultaneity, are really an accident of the fact that the speed of light is so fast. That we think things are instantaneous when they're not. If I take a picture of all of you now with my camera, in fact, I'll do it. I want to get a picture anyway. Okay, there we go. I took a picture of you at that instant, right? But it wasn't that instant, because you're closer to me than you in the back. And that means that the light took longer to get from you to me than it did from you to me. So I took a picture of something that's spread out in space, but it's also spread out in time. The reason we don't ever think that way is the speed of light is so fast that we have this illusion that things are instantaneous. And so it's a property of our circumstances. If the speed of light was 20 miles an hour, we'd all have recognized Einstein to be correct, because we'd be traveling close to that. And in fact, one of the consequences of this theory is the fact that nothing can travel faster than light. The reason being, by the way, that as you get close, faster and faster to the speed of light, things shrink, time dilates, and also it turns out things get more massive. And so it basically takes an infinite amount of energy to push something faster than the speed of light, which is why objects that have weight, and I notice you have weight, Jeff. Yeah, anyway. You can never get them. It takes an infinite amount of energy to push something faster than the speed of light. That's one of the reasons the speed of light is a cosmic speed limit. Okay, now Einstein, I want to push this notion of time a little bit more. Einstein was a patent clerk in Switzerland, and I've spent time in Switzerland and Zurich, well, in both Geneva and Zurich, and I wrote one of my books largely in Zurich. And if you're in Switzerland, the one thing you notice is that the trains are always on time. In fact, before my iPhone, or anything like an iPhone, literally that was a way of telling time. I lived right near a subway station in Zurich, and if the train was at 9 o'clock and my watch was wrong, and I arrived at 9 o'clock my time, but it was really 9:01, I missed that train. And so there's a train from every city in Europe leaving, in Switzerland, basically there's a train leaving every 2 minutes. It's a wonderful, sustainable environment that the United States will never have. It's one of the reasons you realize that Switzerland will be here long after the United States has maybe gone. But this is the view from this Bern, of the beautiful clock in Bern, and he was a patent clerk in Bern. He probably saw this every day right by the train station. So it wasn't surprising when he started to think about time. He started to think about it in terms of trying to explain it in terms of trains. And so just for an example, this is how crazy this idea of simultaneity is. He said, well, okay, I got a train, and I'm a conductor on the train, and I have a bunch of clocks, and I synchronize them all. And they all start ticking, and they're all synchronized, and the train is a certain way. If that train is moving through the station very fast, and I'm watching it from the ground, first of all, I'll see the train being scrunched up, as you can see. But the really weird thing is, I'll also see that the clock in the front of the train is ahead of the clock in the back of the train. Things aren't simultaneous. And so there's now time differences. The time slows down. These clocks are going more slowly than that one. But, these clocks are, for you on the train, it looked like they're going faster. Namely, they're ticking a minute when this one, if you're on the train, it looks like they've ticked a second. So there's time dilation and simultaneity go out the window. Now again, these were all just ideas. And of course, now we've tested all of them all. We know that when you're traveling fast, your clocks slow down. We can measure it with cosmic rays. Maybe in the question period, I'll tell you how we can measure it. And any undergraduate physics student can measure it easily. Clocks slow down. It's really true. This isn't science fiction. It isn't some theory. It is a fact, an experimentally verified fact. Same about mass. Okay? And that's one aspect, but then Einstein did something else. That was the baby part of his theory. He's most well known for that, special relativity. But his real triumph was general relativity. This theory which I talked to you about that said matter and energy curve space. And gravity is just a reflection of the fact that space is curved, space-time is curved. It's crazy. But the implication of that is that actually not just does mass and gravity curve space, but it changes time as well, because space and time are tied together in a dimensional universe. And basically he said, if you're in a gravitational field, if I'm higher than you, and I am right now because you're sitting, my clock is ticking at a different rate than your clocks, because I'm further away from the center of the Earth and the gravitational field is a little weaker up here than it is there. The amount is so imperceptibly small that we never notice it. Okay? But and it sounds, once again, like something so esoteric that when some people would say, who the hell cares about any of this? Here's why you should care. How many people use GPS? Well, I use GPS to come here. Okay? If you're not from here, do you use GPS to get your car? Okay. If you use GPS, I wrote a piece on this, I think for the LA Times when I was stuck in traffic in LA once. I had time to think about it. That our lives depend upon using this very fact about general relativity. One of the most esoteric things about general relativity is that clocks slow down. The experiment that first tested this was when I was at Harvard. My office was in that building. But Bob Pound, who was an older professor when I was there, and postdoc Ripka, 30 years earlier, had done an experiment. That's a little rooftop lab that was built for them. And they said if Einstein is right, the lab is up there is higher than the basement of the Jefferson labs. And if I have a clock here and a clock up there, they should be ticking at different rates. The difference is 1 part in a million billion. So again, you wouldn't think you could measure it. And this is amazing that they measured it because it was in days where we didn't have internet. So there was a radioactive source in the basement that emitted a particle with a certain energy, a very specific energy, okay? And that basically is a wave that's ticking with a frequency. And then and that was Rebka, and Bob Pound was up there actually Pound was in the ground, Rebka was up there. And so basically they used telephones because that's the way you could communicate, and they took data, and what they found was that the frequency of the radiation measured up on top of the building compared to the frequency in the source differed by 1 part in a million billion. Exactly as Einstein had predicted. The Pound-Rebka experiment, a beautiful experiment. Pound never even had a PhD. That's a long story. I'll tell you some other time. But okay, so this really works. Very esoteric, right? But not so esoteric. How does GPS work? GPS works basically by triangulating. Your phone gets a signal from satellites, or a bunch of satellites that have atomic clocks on them, very accurate atomic clocks. And basically, what happens here is you measure what your phone basically gets is a time signal, and it gets the time difference between the signal from this satellite and that satellite and that satellite. But of course, since light is traveling at a constant speed, you know the distance to these satellites. And therefore, triangulating, if you can see 3 satellites, triangulating distance, you find out exactly where you are, right? That's how GPS works. That's why in the old days it used to say finding satellites. Now it doesn't, and it wouldn't work unless you found 3 of them if you're old enough to remember the early GPSs. Okay, and it's better with 4 or 5 or 6. And these satellites are in orbit way above the Earth all over. Some of them are in geosynchronous orbit above the tidally locked in a sense. So they're always sort of the same place of the Earth. But fine, great. Here's the problem. These satellites are traveling in excess of 10,000 miles per hour. So special relativity says they're a little bit slowed down. But general relativity says these clocks are 20,000 miles above the Earth. They're in a weaker gravitational field, and therefore, in fact, it turns out in the opposite direction. They're ticking, in this case, a little more slowly than you'd imagine because of general relativity. In terms of the general relativistic effect beats the special relativistic effect. And if you can show that in a day, and I don't know if I have the number here, but I think it's 38 microseconds per day difference between, I didn't write it down. But you can show that the difference between the ticking rate of these clocks here and the clock in the ground is 33 microseconds per day. But light travels a meter in a nanosecond. That nanosecond is 1 part in a billionth of a second. So it travels 3,000 meters in a microsecond. So if we didn't take this effect into account, your GPS would be off by 33 kilometers by the end of the day. In an hour, it'd be off by a kilometer. So we have to use that effect every day to get here. And you all depend on it. So this esoteric thing that seems like it's irrelevant, the edge of physics, is central to our lives now, those of us who depend on GPSs. So it really works, and it even has a technological application. Okay, so this works, we now understand that this quaint notion that we had that time and space are invariant and absolute is wrong. It's relative. Different observers measure different things. It depends on the gravitational field you're in. And also that's a reflection of the fact that we really live in a four-dimensional universe, just like in Plato's cave. We were seeing the shadows of a four-dimensional universe. When I take a picture of you here, I'm taking a slice in space and time. If I'm moving very fast with respect to you, my slice in space and time is kind of twisted. Okay, it's twisted a little. Okay, good. So now you understand you live in a four-dimensional universe, and that quaint illusion of reality was just an illusion. Now I think I'll go a little bit more, but I'm going to give you a break again. But and we will have time, but it'll all be measured the same because we're not going to. But when Einstein told us that space and time are tied together, there's another weirder effect that many people think about, and that is, look, I can go on a round trip from Prince Edward Island to here and then back to Prince Edward Island. I can travel all the time. You all do this. So if I can do a round trip in space, why can't I do a round trip in time? If space and time are really just interchangeable, shouldn't I be able to go forward in time and then back and come back to where I started, or back in time and then come back to where I started? And it turns out the answer is yes. General relativity, in principle, allows you to do a round trip in time. It allows space travel, time travel, in principle. The question is, does it allow in practice? And the answer is we don't know. Okay, here is an example of a time machine. It's a weird example, but it's nevertheless the simplest one to describe. This is something called a wormhole. I can't draw a curved three-dimensional universe, but I can draw a curved two-dimensional universe. And by the way, I didn't even draw this picture. But so imagine a wormhole is just a shortcut. If you ever saw Jodie Foster in Contact, she goes through a wormhole to get to some very far distance. It's a shortcut through space. So if I want to travel to this galaxy over here, long, long ago, far, far away, I have to go all the way around here. Maybe it's 50 light years away. Maybe let's just make it 3 light years away. Okay? It's not. Galaxies are millions of light years away. But I could go through the background space. But if things were just right, I could create a little wormhole that's maybe a mile long in this direction. And I just take the shortcut through the wormhole and end up here. Okay? So that's what a wormhole is. It's a shortcut through space, through a curved three-dimensional space, this two-dimensional projection of this. But it was realized actually by Kip Thorne, who later won a Nobel Prize for gravitational wave discoveries, that this is a time machine. And I can actually even explain it to you. So the wormhole, you can be at this mouth end of the wormhole or that end of the wormhole. But let's say this end of the wormhole is moving with respect to the background space, moving very fast, close to the speed of light. And it does a circle that let's say 5 light years around. 5 light years around. It's traveling near the speed of light. It takes it 5 years to do that. Okay? Now, because an observer here is moving very fast through the background space, their clocks are slowed down. So that whole trip may just take a week, not 5 years. Okay? So this point here is 5 years minus a week before this clock here. So if you want to go backwards in time, you just go through the wormhole. You come out 5 years minus a week earlier. Then you come back in a rocket ship. Maybe it takes 3 years to get there. You arrive where you started 2 years before you left. It's true. Could happen in principle. It bothers physicists because the paradox is involved, the famous grandmother paradox. What happens if you go back in time and kill your grandmother before your mother was born? Then your mother wouldn't be born, and the people I talked to this morning about my mother, that might have been a good thing. But then I wouldn't be born. I wouldn't be born. But then if I wasn't born, how did I go back in time and kill my grandmother? Okay, and those paradoxes bother physicists. But as I keep trying to remind people, the universe doesn't exist to make us happy. So maybe time travel is possible. And my friend Stephen Hawking used to say that time travel is impossible, and he argued 2 things. He said it's possible. He announced he was having a party for travelers from the future. Okay, and he did the party. No one showed up. He said time travel is impossible. I actually argued. I said that doesn't prove time travel is impossible. Maybe they all went back to the 1960s and no one noticed, because they were weird and the 1960s were weird. But the point is, we just don't know if it's possible. We do know, however, that stable wormholes can't exist if normal matter's energy is all there is. Because it turns out the mouth of a wormhole will collapse to form a black hole in a time scale much shorter than you can time it takes to travel through it. There are no traversable wormholes if normal matter and energy is all that exists. But if there's a very special kind of energy, you could have a wormhole. The question is, can you create that special kind of energy? And we don't know. Most of us are betting you can't because of the paradox of time travel. But it's an open question at the forefront of physics. So all of that little thinking, starting back with Faraday and Maxwell and jumping frogs, has taken us to time machines. And in fact, we may live in a universe where time travel is possible. We just don't know. And we have to give up our quaint notions of little things like cause and effect, if it is. Okay. Maybe we'll take a break. I've been about 45 minutes, okay, or a little less than that. And I want to change things completely to talk about how the world we're living in is really just like living inside one of those crystals. And then it's simple. Then we'll just do quantum mechanics in a few minutes with some, well, I have some magic tricks for quantum mechanics, so there's no thinking involved. And then we'll end up with consciousness, which may be even more useful for leading to. So let's take a break for 10 minutes. Does that sound okay? Okay. Okay. I gave you the example at the beginning about living on a crystal, and in a sense, we all do. And it harkens back to a discovery was made in 1911 by accident by a guy named Kamerlingh Onnes. He discovered when he cooled mercury down to a very low temperature, 4 degrees above absolute zero, minus 350 degrees Fahrenheit or something like that. I don't ever use that system of units. So something really strange happened. You could measure the resistance. Resistance, of a wire, and it heats up when you put a current through it, and that depends on its resistance. What he discovered, to his amazement, is when you cool it down below a certain temperature, a critical temperature, in that case it's 4.2 degrees above absolute zero, the resistance goes away. It doesn't come small. It goes away to zero. There's zero resistance. You start a current in a wire of superconductor like mercury below this temperature, you come back 1 million years later, it's still flowing. It hasn't lost any energy. There's zero resistance. This was magical and unbelievable, and it's a property of quantum mechanics, it turns out. I won't go into why, but it is. And it looked like it was just a freak of nature. But of course, now we use superconductivity a lot. The Large Hadron Collider at CERN couldn't function if it weren't for superconductivity because it has huge currents to create this accelerator. Those currents would burn the whole place down, except the whole thing is cooled so that you have superconducting wires. And then you can create huge magnetic fields and it doesn't heat things up. And in fact, there's huge amounts of liquid nitrogen flowing through the superconducting coils in CERN, and it would be a disaster if it was called a quench, if there was a leak and you lost the liquid nitrogen, because suddenly we'd heat up, and suddenly that current would suddenly have resistance, and a huge amount of energy it would be almost the energy of an atomic bomb. I mean, that much energy would be released. Maybe not quite as much, but it'd be a disaster. So you have to make sure that that's happening. But we use it, superconductivity, not as much as I kind of thought we would when I was younger. But one of the big holy grails of physics is to try, not to find a material that isn't superconducting at 4.2 degrees above absolute zero, but a superconductor that's a thing that's superconducting at room temperature. Because boy, wouldn't that change technology? You'd want to invest in it and stuff. Yeah. Okay. Now, one of the weird things about superconductors, and we do this in undergraduate physics labs, is something called the Meissner effect. Here's a liquid dry ice, and you have a superconductor in there. And what happens is if you have a magnet, and you try and bring it near a superconductor, it levitates. That's because it turns out magnetic fields cannot pierce a superconductor. So if you think those field lines of Faraday, they get repelled away, and you try and press it down, and the field lines get squished, and it produces a pressure and keeps it up. Magnetic fields cannot permeate a superconductor. Now, we understand that now as follows. This is the little bit of tricky stuff. Light travels at the speed of light, as we've established. The reason it does is because light doesn't have mass. Nothing that has mass can travel at the speed of light because it takes an infinite amount of energy. But if you have no mass, you can travel at the speed of light. In fact, if no mass, you can't even travel slower than the speed of light. If you have zero mass, all you can do is travel at the speed of light. Okay? It turns out, therefore, that the speed of light is what it is, and also electromagnetism is a long-range force precisely because the particles of light, called photons, have zero mass. Accept that for the moment. It's a property. Light is a long-range force, or electromagnetism is a long-range force, because the particles of light have zero mass. Okay? Light is the thing that conveys electromagnetic fields from one place to another. So you can understand what happens here is that it turns out inside a superconductor, things are arranged in a very weird state, and when you have electromagnetic fields that try and propagate into the superconductor, suddenly light gets a mass. And because it becomes massive, a force that's propagated by a massive particle is not long range. It dies off exponentially. So the reason that the magnetic fields can't pierce a superconductor is inside the superconductor, light has mass. Weird, but true. Now, what would it be like if you lived in the superconductor? If we lived in the superconductor and did physics classes, we'd say, okay, we found the laws of electromagnetism. Light is mass, the electromagnetic field is short range, and the laws of physics would be very, very different. An accident of our circumstances. We don't live in the superconductor, so we feel we're really smart, and we know that light doesn't have mass. It's just these stupid people in the superconductor, they don't know any better. Okay? Well, that's the world we live in, because it turns out we live in a superconductor. This guy, Mr. Higgs, was thinking about, in this case, not superconductors, although the mathematics came from someone who, exactly, Philip Anderson, who won the Nobel Prize for something else. But he had thought about that analogy. He's the one who more or less, he showed how light got a mass inside a superconductor. Okay, that's not what he won the Nobel Prize for. But Higgs was thinking about that in the context of particle physics and relativistic quantum mechanics and all this neat stuff. And he realized, well, if, in a superconductor, when you cool mercury down, a very special state is created when it's superconducting. Okay? If you cool the universe down, maybe a very special state exists in nature. Okay? And we're traveling through that special state. And the properties of the things we see are just a property of that accidental special state of the universe that it happens to be in right now. And one way of thinking about it, this is the picture I gave you earlier. One way of thinking about it, this is the language called Feynman diagrams, or Dick Feynman, who won the Nobel Prize, not just for Feynman diagrams, but this helped us understand physics. He said, well, let's say you've got the way to think about this, some particles moving along, but there's some background field that exists everywhere, some weird configuration that we can't see, but it's there. And particles kind of scatter off it. And when they do, they get some resistance to their motion. And they act like they're massive. And so the particles behave like they have mass because they're interacting with this field. It's really just like the idea of you're a swimmer. You're swimming really fast, okay? Fill the pool up with molasses. Try and swim in it. You feel a lot heavier. There's a lot more resistance to your motion. Or another example, you're driving your car here in the middle of the night like I was when I first came here, but as I didn't do happily, I didn't go off the road. Or let's say I run out of gas, I push the car to the side of the road. I can push it if I'm lucky. But when I get off the side of the road, it's in mud and I can't push it anymore. Cars suddenly become more massive, or it seems like it. And he said, well, the mathematics says it's possible that the world could have this background field, and guess what we call it, a Higgs field. And really what we're measuring is the mass of particles as an accident of our circumstances. Well, that's a nice part. He wrote it down. Most people ignored it. An interesting idea, 1964. One-page paper. But then, it was realized that this simple idea might describe the universe we live in. This is some Feynman diagrams. This is electromagnetism. We see electrons repel each other because they exchange particles called photons. And this is a picture of this virtual photon that's exchanged. I remember talking about virtual photons. We can understand all of electromagnetism, the quantum mechanics of electromagnetism. We call it quantum electrodynamics, the theory that basically Feynman helped develop in its final form. And all of it can be understood as the exchange of photons. And electromagnetism is a long-range force because the photon is massless. Because I told you that before. You remember that. Well, there's another force in nature. It happens inside nuclei. Only inside nuclei. It's called the weak force. And it changes neutrons into protons. It's responsible for radioactive beta decay, radioactive processes that we measure. But all of this happens inside the proton. We can think of it in a Feynman diagram that looks very similar. Now it's not just the exchange of a photon, it's weird particles called intermediate vector bosons. Okay, it doesn't matter. But we can understand this force as it looks very similar, except there's a big difference. These particles are very massive. The theory, if you want to just present it this way, you say, well, how massive would these particles have to be to have the properties that we see? They'd have to be about 90 times the mass of a proton. Really heavy. And this theory was predicted first in 1961, then again in 1967. Because the theory doesn't work. It turns out you can't, if you try and write the mathematics of a theory just like this with massive particles, you get infinities, you get singularities. Someone asked me about singularities. You get nonsensical results. It's a big problem here. But what was realized by two people, Steve Weinberg and Abdus Salam, is that maybe in a fundamental sense, all of these particles are massless. They have zero mass. Then the theory works fine. Gives you the right answers. But hold on, these guys, and we've now measured them and discovered them, and they're massive. They're 90 times the mass of a proton. But maybe they only get a mass by accident. Maybe there's a Higgs field in nature, and the W and Z particles interact with that Higgs field and act like they're massive. They're really massless in a fundamental sense. And the photon doesn't. Then I can unify these together in a single theory. We now call it the electroweak theory. They're really different manifestations of the same force, but they seem so damn different because of the accident of our circumstances. We happen to live in a superconductor. And the W's and Z's are something like a superconductor. The W and Z particles interact with that field, act like they're massive. The photon doesn't, acts like it's massless. And that's why electromagnetism is a long-range force, and the W and Z and the weak force is short-range. And we, just like those people in the superconductor, say, well, they're very different theories. They're very different forces. But if we were somehow able to look from the outside, say, you're just idiots, you don't realize that it's just an accident, that really the W's and Z's are just like the photons, but you live in a superconductor, and you have this illusion of nature. Okay? It's exactly the same. We felt really proud of ourselves for being so much more smart than the people who live in the superconductor, but we've now realized, just like that what we're seeing are the shadows of reality. The reality underneath is, in fact, one in which all these particles are massless. But there's a Higgs field in nature. Sounds good, nice story, but physics isn't a story. Religion is. Physics makes predictions, and they're wrong or right. And if they're wrong, you throw out the idea. So, okay, it's nice to have this. Oh, these guys, my friend Steve Weinberg, Sherry Glashow, and they won the Nobel Prize in 1979 for that. Let's talk about sadomasochism. So it's a nice idea, but ideas don't matter. Mr. Higgs didn't win the Nobel Prize for having that idea. He'd win the Nobel Prize, which he eventually did, because it turns out that theory predicts that if there's a field, for every field in nature, quantum mechanics tells us there's particles. There must be Higgs particles associated with the Higgs field. Well, how could you see them? Well, if the vacuum is full of this field, all you have to do is spank it. Spank it hard enough, and you kick out the particles. So you turn the picture, the Feynman diagram I gave you. Here was the Higgs field interacting with things, right? But let's turn the picture upside down. Let me give a particle accelerator and have two particles collide and spank the vacuum hard enough, and you'll produce a real Higgs particle. And that was the idea. And for 40 years, we kept trying to spank the vacuum hard enough. And we did because we didn't. The theory's nice, but it doesn't tell you what the mass of the Higgs particle is. Turns out it can be almost anything. And every time people would say, oh, I have a theory that predicts the Higgs mass is this, and we do the experiment, it wasn't there. It wasn't there. Till July 4th, 2012, at the Large Hadron Collider, where we discovered it. And the point is, it's more than just a story, because you can make all sorts of specific predictions about how you're going to produce it in an accelerator, and the accelerator can look for it, and there's all these processes that don't matter, but these are the processes that would produce the hypothetical Higgs boson if it existed. These are the particles that we look for, and this is the Large Hadron Collider, the superconducting collider in here, and there are particles going around 26 kilometers in one direction, protons, and in the other direction, protons are going around at nearly the speed of light, going between Switzerland and France, thousands of times per second without passports, and here it is. Here, if you ever land at the airport in Geneva, the collider is right underneath the ground, right near you, and this is the Celeb, I think, and well, no, it isn't the Celeb. It's the other mountain. But anyway, France is like right through there. I spent a year at the Large Hadron Collider. It's a nice place to visit if you have a chance. This happens to be the image of somewhere in this. These are the particles coming out. This was a picture that told us the Higgs existed. Turns out when you understand that. And as I say, it's not just a story. You make predictions about all the different processes that the Higgs, if it's going to, this Higgs going to do this, all the way the Higgs is going to decay. You make predictions, and again, you measure it, and then things. We now know the mass of the Higgs. It all works. And there's always outliers, but that's statistics. And so this is science. It's not a story. You make the prediction. We know it's the Higgs. Well, at least it walks like a Higgs and quacks like a Higgs, so it's probably Higgs. Okay. So. What was the capstone? Oh, yeah, that's finding Mr. Higgs and another person who'd also done the similar idea, won the Nobel Prize. Peter just died, and I wrote an obituary for him recently. But he said it ruined his life. He was a lovely man, a quiet man, and when it won the Nobel Prize, he said it ruined his life because his life was no longer quiet. And so he died at, I think, 92, age of 92, about a month ago. So we are living on a crystal like that. What we see, because think about it, it's like, remember the laws of physics are different in that direction than those directions if you live on the crystal? That's the way it is for us. The laws of physics are different for the W particles than they appear to be for the photons. But if you could stand outside, you'd see, well, that's just a property of the accident of your circumstances. The world we see, and it turns out it's not just W's and Z's. It turns out the mass of most particles comes from the Higgs mechanism. Particles are heavier if they interact more strongly with the Higgs field. Particles are lighter if they interact less strongly, but at a fundamental scale, they're all massless. And of course, if particles just remain massless, we wouldn't be here. There'd be no mass, there'd be no stars, no galaxies, no people, nothing. Everything we see is possible because of that accident, of that illusion that's created that we're massive and that particles have different masses that allow us to exist and have our happy lives, our happy, ignorant lives going through. And then we've discovered it's just an accident. So another illusion. Quantum mechanics. Now, to do quantum mechanics justice, I would have to give you a whole lecture and you wouldn't understand it anyway. Because quantum mechanics is not understandable. Because we are classical beings. We can't intuit. The predictions of quantum mechanics are really weird. There are three kind of examples that are really weird. Entanglement, collapse of the wave function, and something called tunneling. So I figured, since I can't really describe the illusion, I'd at least give you some illusions that describe it. So I thought I'd do 3 magic tricks to break the ice. Okay, let's see. Oh, Jeff, why not? You're so much fun to make fun of. Come on up.
Bring my money?
No, the money is for the next trip. I'm going to use you a lot. Well, okay. Well, you can sit there. Actually, it's all right. Stay down. Okay. This is my favorite way of getting you to pick a card. Just, again, cut the deck a third of the way down and turn it around. And then cut the deck a third of the way down. 2/3 of the way down. 2/3. Got it? Okay. And then, okay. And we'll look to see where the cards turn over. Okay, here. Now, take this, but don't look at the card. Okay. If this is a quantum mechanical deck, as it is, in fact, then quantum mechanically, classically, he has some card and it has some value. We all believe that there's a card and has some value, but he hasn't looked at it yet. If he hasn't looked at it and it's a quantum mechanical variable, it can have any value. If an electron, for example, is spinning, and its spin point, it turns out its angular momentum points in some direction. You can measure it. It points in that direction, or this direction. Before you measure it, it's spinning in all directions at the same time. Like it or not, that's what it does. So if this is a quantum mechanical deck, he hasn't looked at it. That card has every possible value, 52 values. It's not determined. The minute he looks at it, however, it's going to, and he can be an Alpha Centauri, and my deck of cards can be here on Earth. The minute he looks at it and sees what that card is, it determines what card isn't in this deck. So that card and this deck are entangled. And it's instantaneous. The minute he looks at it, before he looks at it, it can be anything. And I haven't looked at this deck, and that card literally is taking all values at the same time. The minute he looks at it, it determines what card it is. It determines the property of the deck. And instantaneously, it seems like communication is going faster than light. It turns out it's not communication. But that quantum state of that particle, which is changed by his observing it, changes the quantum state of this. So you look at your particle, look at it, and instantaneously I know it's the Jack of Spades. Am I right?
6 of diamonds.
Is it? Okay. Okay. So that's entanglement. Okay. Let's try collapse of the wave function. I should have known better than ask you to do that. This is their favorite trick. This was your favorite trick, so I'll do it with Cyan a bit. So this is this is a trick I did for them, but I like to think of it as collapse of the wave function. Okay. 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 Yeah, because you already have. Okay. Okay. Great. What's your name again?
Mike.
Mike. Okay. Mike. Okay. So here is an invisible deck of cards. You can take it. Take it. It's in a box. Open it up. Take out the box. Take the cards. Don't be afraid. Here we go. Okay, put the box down here. It's very special. Okay, look at the cards. Okay. Okay. Right. Pick a card out. And you know what card it is?
No.
What? Well, sure you do. You can see it. Tell me what card it is. Okay, don't tell me what card it is, but pick a card. Okay, you know what card it is? Think of it in your mind. You got it? Okay. So you know what card it is that you picked with your mind. Turn it around so it's facing the opposite direction of the other cards. Now put it back in the deck. Put the deck in the box here, very carefully. Thank you. Okay. Magic deck of cards. So now, it turns out it's magic because when I put it in my pocket, it turns into a real deck of cards. Okay. But it's still any value, right? It's that card which is turned over the opposite direction could be any of the cards in the deck. What was your card?
Want me to tell you what
Yeah,
it
I do. That's why I asked. Yeah.
is? King of Hearts.
King of Hearts. Okay. Well, so now the wave function is collapsed. This deck of cards had the card that was turned over had all possible values. But when you tell me what it was, the wave function was collapsed. So now just one particle should be turned over because the wave function collapsed. It was the King of Hearts. So one card should be turned over. Can you look at that? There's one card turned over in this thing. See what it is. You never know. Oh my God, it's the King of Hearts. What do you know? Okay. Collapse of the wave function. That is one of my favorite tricks. Okay. Now, let's take that deck we had before, that quantum mechanical deck. And it's a very special quantum mechanical deck because it illustrates the last property of quantum mechanics, which is tunneling. If I could, Jeff, I want you to run towards that wall with your head and crash into it as fast as you can. Okay, we're not going to do that.
You want me to do it again?
Yeah, that's right. Exactly. Perfect. Excellent. We don't want Jeff to do that because we know what's going to happen. From now till kingdom come, he could crash in that ball, and all he's going to do is create a headache and get bloody. But if you're an electron, every now and then, an electron goes through a barrier or an elementary particle, and the laws of quantum mechanics, because they operate on very small scales, say that when a particle, it actually can go through the barrier. Classically, it's impossible. But quantum mechanically, the particle tunnels through the barrier with a very small probability we'll get out. That's what is responsible, by the way, for nuclear fission. Particles inside the nucleus. With a very small probability, a particle can tunnel outside the nucleus and escape, and that creates a radioactive fission. Can you get that dollar bill I gave you earlier for being so much better at golf than you?
You don't explain why I have this dollar?
Yeah, well, I made the mistake of doubting myself. Is that right?
Doubting me.
Yeah, I doubted you. Okay, he told me that I would shoot better than I did, and I shot better than I did. So let's see. I hope that you haven't ruined it. So, okay. So I'm going to try this. We'll see if I can make it work. I don't know. We haven't tried this in advance, again, don't try this at home. So that deck is quantum mechanical. So of course, a classical bill cannot go through the deck, right? Cannot tunnel through the deck. But in principle, maybe if I'm lucky, maybe if the deck is just right, I can take that bill and put it through that solid deck of cards because it's tunneled through. Now, that's classically impossible. But it's even better because when a particle decays due to radioactive processes and tunnels out of the nucleus, it does more. It gets out, but it changes the property of the nucleus. The nucleus decays. So in the process of tunneling, it's changed the properties of this deck of cards. And what it did, when it tunneled through, it changed it and turned it into a solid block of metal. Isn't that weird? That's one of my favorite tricks.
I wanted to change the dollar bill into $100
Yeah.
bill.
That's the first time I've ever done that trick, and I love it. And actually, it's a trick I did learn from my friend Pendulet. But isn't that a great trick? Yeah. Okay. You can examine it later. It's a solid block of metal. Isn't that wild? And it was only possible because that was a quantum mechanical deck of cards. If it was a regular deck of cards, it wouldn't be possible. So that's quantum mechanics. I told you, we have a little fun instead of worrying. But it's just weird, accept that it's a weird. And the real world, at a fundamental level, is weird. But it's weird to us because we live at a classical level, and we just happen to have this accident of our circumstances that we're very large compared to the scale where quantum mechanics normally operates. If we weren't, then quantum mechanics would be sensible. Now, one of the neat things about modern technology is we're extending the quantum world to involve larger and larger scales. Quantum computers, we're using the weird properties of quantum mechanics and trying to exploit them to make new technologies, and they will change the world in the 21st century. And some people anticipate it and support it and make money as a result. Okay? Anyway, quantum mechanics. Last thing, so the classical world we experience is an illusion. So we talk the illusion of time, the illusion of matter, the illusion of the classical world. The last illusion I want to talk about, and this is good because actually it's great. I'm only going to give you another 45 minutes. And this happens to be from my new book, The Edge of Knowledge, is the hardest one. It was the last chapter of my book because it's so much harder than physics. Consciousness. I'm a physicist because it's so much easier than biology. Consciousness is in some sense the ultimate illusion, you might think. We have consciousness, but what is consciousness? And I spent a lot of time. One of my favorite quotes comes from a physicist, Erwin Schrödinger, who said, consciousness is a singular of which the plural is unknown. Part of the problem of consciousness is most of us are conscious, not everyone, but most of us are conscious. And I won't name names. But, and so we kind of know, it's like pornography, you know when you see it, right? Like that judge said. And but what is it? We know we have our sense of our own consciousness, but what does that really mean? We can't ask animals if they're conscious. My dog seems conscious to me. My dog looks like he's guilty when he's done something wrong. He looks happy when I'm home. Is that anthropomorphic? Is that real or not? So the problem of understanding consciousness, we have one example of it that we can probe. But even that example is not a good probe, as I'll show you. So I don't want to spend a lot of time, but I spent a lot of time trying to figure out what was thinking about consciousness, and spent a lot of time with neuroscientists and stuff. And not surprisingly, my presumption was correct. We don't understand it at all. In fact, one of the ways you can know we don't understand it, someone once told me you can tell how much we understand something by how many books are written about it. There's a new book that comes out every week about consciousness. That means we don't understand it. Okay? There's only one book about quantum mechanics you need. Dirac wrote it in 1930. You don't have to write another book. Okay? So if you really understand it, one book will do. When you don't, everyone's got their own theory, and that's why there's so many books on consciousness. But if light, you try and define life, consciousness is much harder. In fact, most cognitive scientists don't even define definition. They just work to explore what the features of consciousness are. But unlike legs or fins, one can objectively measure cognitive developments in long extinct species. Obviously, there's an evolutionary basis of consciousness. We took a long time for us to get here on the evolutionary change, and there are many aspects of cognitive psychology that you can understand from evolutionary psychology that are remnants of our evolutionary background. Xenophobia, all sorts of things that appear to have useful evolutionary purposes that sometimes are now not particularly useful, but they're remnants of that. And as I say, even in extant species, there's no direct probes of consciousness from different species. They're probes of behavior. And you might think behavior tells us about consciousness, but it really doesn't. I don't know if my next slide is there, but you can't infer consciousness from behavior. Protozoa can swim away from harmful environments. And even bacteria give some behavioral evidence of learning and memory, but they don't even have neurons. So no one's thinking protozoa, well, except for maybe Deepak Chopra. No one is thinking that protozoa or amoebas or bacteria are conscious. Okay? So you can't necessarily infer just from behavior that something is conscious. That's why when my dog has a certain behavior, I might infer that to mean it has consciousness, but I have to be very careful and ask myself, am I really just anthropomorphizing? Is it really conscious, or is it just some instinctual biological reaction? We don't know. And people have very different views of it. One of the reasons I'm a vegetarian is I kind of accept, and Peter Singer, who was very influential in that you might say, for me, the question is, what can animals suffer? Can they feel pain? And it certainly appears that it's for a certain large segment of animals that they can suffer. And for me, that's why I don't eat meat. Okay? That's all. One of my favorite quotes is from Bertrand Russell, which is from the protozoa to the man, there's nowhere a very wide gap either in structure or behavior. And it's probably true when you think about it. People are on large scales are just no more wise than protozoa. And the upcoming American elections are a clear example of that. In our own species, we can't even trust our own perceptions of consciousness. And this is one of my favorite experiments. It was a split brain experiment done by Michael Gazzaniga and others a long time ago. So we have two hemispheres in our brain. And they're connected by a corpus callosum. Women have larger corpus callosums than men, which is why my wife says women can multitask better than men. I don't know if it's true, but that she keeps telling me. Now, interestingly enough, the way it works is, our right visual field is processed in the left hemisphere of your brain, and our left visual field is processed in the right hemisphere of the brain. Same with motor control. Left body motor control is processed in the right part of my brain, and right body motor control is processed in the left part of my brain. The great thing about this, so it turned out for certain epileptic people, there's an operation, you can sever the corpus callosum. It doesn't really produce that, it doesn't hurt them a lot in any way. I mean, they behave normally, but the seizures die down. And it's a procedure that's still used. But of course, it gives you, if you're a psychologist, a great set of subjects for experiments, because these people, the left part of their brain doesn't communicate to the right part of the brain. And Michael Gazzaniga and colleagues did this great experiment called split brain experiments, where they put such people in a room with a screen, and they could see images with the right eye and the left eye, separate images. Okay, but the parts of the brain couldn't communicate to one another. So what happened is in the left side, they projected a snowfall, and the right side, a chicken claw. And then they gave people, with their left hand or the right hand, they could pick, various plastic toys to represent the scene they saw. And since the left hand sees the same thing as the left eye, it plays, so the left, with your left hand, they picked the snow shovel. And with the right hand, they picked a chicken. Okay? But your speech processing is only done in the left hemisphere. So when you're talking, and your corpus callosum is severed, you have no idea what was being processed in the right hemisphere. So they'd ask those people who had done this, their hands could do it, their eyes could do it, they asked them, why did you choose these?
And the answer was, the chicken claw goes with the chicken, because that's the left hemisphere, right? You can see what's in the right hemisphere. And you need a shovel to clean out the chicken shed. Because linguistically, they had no idea there was their linguistically, and we were talking about linguistically, their mouths did not know that they'd seen that the brain had seen a snowfall. So their whole consciousness, they gave an explanation. And they were perfectly happy with the explanation. It worked for them, but it had nothing to do with reality because of their consciousness was determined by this weird property of their brains. So even with humans, you cannot trust what they say about why they're doing what they're doing. You cannot trust that because it's filtered in your brain to produce a conscious statement, but you can't trust that that conscious statement represents the reality behind what people are doing, what the ultimate consciousness is. As far as their arms and their eyes are concerned, the consciousness is very different than their mouths. Isn't that wild? Okay. The verbal left brain created a coherent story of conscious awareness that had nothing to do with the person, what the person actually saw. The brain rationalized the choices to explain behavior, communicating a false narrative because that was the only narrative that made sense for the left hemisphere. Okay? Think about that when you think of yourself as a rational being. So, we all sense a sense of self with it. So a lot of people say self is an illusion, and maybe you'll talk about it, I don't know, but so Buddhists might say something like that. It doesn't mean much to me. But yeah, philosophers claim self is illusion. Like some people say time is illusion, and I say to them, okay, you miss your 10:20 train and you get to work late and tell me it's an illusion. Okay, similarly, I find that to be a little utility because anyone who's just been kicked in the shins or jilted by a lover, consciousness means a lot. Okay, sense of self means a lot. So maybe it's an illusion, but that doesn't matter. The question is, how does that illusion arise? That's what I was talking about, the physics. The world is an illusion. Physics has taught us how all those illusions arise. It would be nice if we had a theory of consciousness to tell us how those illusions arise. We don't. It's much harder. Much harder. That's why I do the simple stuff, the physics, okay? The key question, yeah, what creates a sense of self? And we don't know the answer. We just don't know. We don't even know it's the right question. My friend Noam Chomsky and I've had discussions where he said he thinks the whole idea of this discussion of self and consciousness is a red herring. Eventually there'll be some mathematical description that doesn't relate to any of that. Maybe he's right. He's been right before. But one of my idols, Richard Feynman, once said, he actually said to me, he said this to me, but he said, he who can do nothing knows nothing. Okay? Keenan, the engineer, Keenan isn't here this morning? Okay, he can do a lot, so he knows a lot. But after Feynman died on his blackboard, there was this statement, if you can't build it, you don't understand it. So maybe the way we'll understand consciousness is not by trying to understand ourselves, but by creating consciousness. And you can, maybe ChatGPT 50 or quantum computers, people talk about all this stuff. Maybe they'll be self-aware, conscious systems, that at least as far as we can tell, are self-aware and conscious. Again, it's going to be an interesting question if you can determine that. There's a lot of hoopla and a lot of money being made about these large language module things that appear to be smart. They're not. Okay, they just are very good at sifting information and filtering it. Okay, and that's one thing. So they can give you answers, but to me, the real thing is coming up with the questions. That's the important thing. And so I think when things come up with questions that are interesting, that'll be much more, and I'll be fascinated personally if there's computers that can, I'll be interested to know if the physical questions that a self-aware AI has are the same as the physics questions I have, or whether they find it very different and their questions are very different. If they're a quantum computer, one of the reasons Feynman helped build quantum computers, or at least propose them, was he said, maybe it'll help me understand quantum mechanics. Because they'll be using quantum mechanics to think, if you want to say. They already do. They can solve simple problems, quantum mechanical problems that we can't solve, because they're using quantum mechanics to solve it. We use classical mathematics to solve it. And so it'll be very interesting. They're already teaching us about small molecular systems, but they're far away from being able to teach us other things. But maybe a self-aware quantum computer could teach us exactly about quantum mechanics in a way we don't understand. I'd love it. But a lot of people are worried about all this. They're saying, oh, okay, this is just going to destroy the world. And I like history. I told some of you I did history before I did physics. And I like to think of object lessons from history. And so let's go back to the 9th century. Okay, back to Plato, in fact, before that. So in the 9th century, a derivation of the Phoenician alphabet introduced into Greece evolved over the next few hundred years. The first time a written alphabet had been bound to be used. Okay? What happened? The really smart people at the time viewed it as a disaster. It was going to end the world as they knew it. It was going to end literature and drama. Plato said writing was an impediment to wisdom. It did not capture the whole truth, and it propagated the illusion of knowledge. It would eliminate the need of memory, because if you could write it down, you didn't have to remember stories, and remembering stories was the key to the cultural environment in which he lived. And so writing was going to destroy that, because you don't have to remember things. You just look it up. Okay? Socrates was suspicious of writing, argued that written communication would never be as clear as face-to-face communication because you couldn't ask questions of a document. And that's, I was talking to Cyan, one of the reasons I think, and I'm happy to say this over to you, why I think TED is a bogus piece of nonsense, is it involves a lot of people giving talks without you ever being able to ask questions. And it's the questions, and hopefully at the end of this, it'll be the questions that will really illuminate things. Okay? But anyway, so they all viewed it as the end of literature, the end of knowledge, the end of wisdom. Okay? But AI, like writing, is just a natural product of human development. It's technology. Writing was technology. Technology is a human invention. It always changes the world. And it always requires humans to change with it. We're different people, not just because we all stare at these 40 years ago. No, I remember the first time I was in Japan, I see everyone doing this. They were playing games, video games. Right? And it seemed like I was on a different planet. Japan always seemed like a different planet to me. Now, I go to Japan, I see that, but it's the same in a New York subway station because everyone's staring at the little box. But it's, not just that. Use an elevator. We all trust the elevator is going to take us to the right floor. That's AI. But we don't mind. What? You don't trust it?
No, it's mechanical.
No, but it's a little computer that tells you press that button, and the little computer tells the mechanical elevator where to go. Have you ever worried about whether it'll take it to the wrong place? No, because we accept it. Okay? So I would argue it's nothing new. And I'm not as worried about AI. I mean, I know there are things to worry about, but I would say that a world of books to read is better than a world without books. I'm an author, so I'm biased. But I would actually change this. A world of books to buy is better than a world without books. But an AI future could be better or worse than the present. Who knows? We should, of course, think of the problems. Recognizing that we don't know whether it's going to be better or worse can help us ensure that the future may be better than the past. Because if we think about the possibilities, fortune favors the prepared mind, as Louis Pasteur said. But thinking about the realization that we don't know is the beginning of science and the first step on the road to wisdom. In fact, humility and honesty demand that we be clear about the limitations of our knowledge. And I've tried to illustrate some of them here. We shouldn't be shy about it. We should celebrate it. We should celebrate the fact that we don't know everything because it means there's something left to learn. It's job security for us, physicists anyway, or cognitive sciences, whatever. It means tomorrow there's the opportunity to learn something we didn't know today, and that's what makes life worth living, in my mind. There remain remarkable mysteries to be uncovered. And the three most important words in science, this was the beginning of my new book, the first sentence in my new book, were the three most important words in science that I don't know. And I think we should embrace that ignorance and enjoy it and celebrate it and realize how much there is to learn about this illusion of reality that we are also complacent about, and that we should be willing to be surprised and amazed and in awe of the real world and realize our perception of what's normal is just myopia. So I guess I will end with another philosopher in deference to Jim, Virgil, sort of a philosopher. He said, "These are the tears of things, and the stuff of our mortality cuts us to the heart." And that's how I'll end. Thank you.
Lawrence, could we go to a dark screen for the close? Maybe the
A
previous
dark
one?
screen. Okay, let me see if I can find a dark screen. Oh, maybe this will be, yeah, okay.
There you go.
There we go. Is that better?
Perfect.
Okay, good.
Thank you again,
We
Lawrence,
ended early.
for a wonderful presentation. You've given us a lot to think about, and I definitely have a few questions for you.
Good, good. I enjoyed it myself, actually. I didn't know how to go, so it was fun.
Oh, good.
Especially the magic tricks, so that was good. Okay.
So I want to start with confabulation. So the idea that we are constructing a narrative after the fact to make sense of things, even though that might not be what was in reality. Two other experiments that I think illustrate that really well. One from Dan Dennett. I don't think he actually conducted the experiment.
No,
but
he didn't
wrote
conduct
about it.
experiments. He wrote about it.
Yeah, and
That's
it
because
was.
he was a philosopher. Anyway, go on.
So he wrote about a experiment where they had people sit with their head kind of in a box so that it was dark, and it was a computer screen in front of them. And in one corner it would flash a red light, and then in the other corner it would flash a green light. But it was done at a speed at which the way it appeared to the person watching it was that it started as a red dot and it moved across the screen and gradually became
A blue dot.
Blue
Or
dot.
red, green dot.
or whatever the other
Whatever.
color was.
I'm colorblind, so it doesn't matter. The same.
Yeah. So what I found fascinating about that is it's illustrating one thing as well, is that there's a buffer.
Yeah.
Because in order for your mind to construct the narrative that there's a line and it's gradually changing color means you had to know what that final color was before the final dot, before the line gets there. So there's some type of buffer between the input and what your brain constructs as the narrative of what happened.
Yeah, but I mean, that's right, but there's a much more simple, well, I don't know, it's much more simple. That's really good, but the whole reason movies work is because we have a buffer.
Yeah.
And, 1/25th of a second, you retain the image so that you could, as long as you're faster than 25 frames, actually 1/16th of a second, as long as you're faster than that, it looks like a continuum really instead of just a bunch of images.
Exactly. So the buffer is important because it's not a direct response.
Yes.
It's a constructed response.
Yeah.
The other thing that I found really interesting was a study, and I don't recall who came up with this one, is they hooked up the people's brains to scanners that could tell what parts of the brain were active, but they were also using TMS, transcranial magnetic
Yeah,
stimulation,
yeah.
where they can actually shut off portions of the brain temporarily. It doesn't hurt anything. And they had them.
And that happens when you wear one of those Make America Great caps, I think that
Is that what happens?
Yeah, it shuts off part of your brain. Anyway, sorry.
Subversive technology.
Yeah.
So
Anyway.
in the experiment, they had to make a decision about which button they were going to push with either the left or the right hand, and then they would push the button. And they could see when they were going to come up with the idea to press a button, and then they would press the button. Now, nothing terribly exciting there. There is some thought that maybe there was an awareness of, they could tell from the brain that it was happening before the person was consciously aware, been disputed somewhat. But the unique thing with this experiment was that using the TMS, they were able to actually trigger the other part of the brain. So if they could see that they were getting ready to push with the right button, they could switch a switch so that the brain would stimulate them to use their left finger instead of their right finger.
Oh, neat. Okay.
Right? And so then they would ask them, you would think if you were getting ready to click your right finger and all of a sudden you did your left, you'd be going, whoa, what happened? Why did that happen? And nobody noticed. And it seemed completely normal. And if they asked them about it, they would just say, well, I just changed my mind.
Just decided last minute, and which is a wonderful experiment, and one of the many examples of the fact that free will is an illusion. I've just had Robert Sapolsky on my podcast and a friend, and in fact, it's too late because it's sold out. But we have my foundation takes trips. The next one is to Bhutan. And Peter Singer and Robert Sapolsky will be on the trip, so you could spend 10 days talking to them about free will. But we have this illusion that we're free to make decisions when, in fact, we're not. Free will is an illusion.
So here's the thing. If all this is bubbling in the background at an unconscious level and something happens, we behave, then we come up with a narrative. Our whole conscious portion might simply be kind of like a press secretary that is coming up with an explanation for what happened that we tell ourselves.
We call it a rationalization, right? I mean, we didn't have the word for it, but it could be that you're right, everything we see and that film that we're putting together in our minds that we call awareness and consciousness is something that could be made up afterwards, and we rationalize what we see to make sense of it.
Yeah.
And we make a narrative that may not have anything to do with really what's happening. So that's the strange thing about consciousness is, we see the final narrative, but we can't see all the bells and whistles in there. But with the experiments that you're talking about, and that's why it's so exciting. As you can manipulate, people that way, we can begin to learn little bits.
Yes.
My suspicion is because of the complexity of the brain and our limit, we probably will limit what the kind of experiments people can do on humans. That's why I'm saying we may need artificial systems which we can manipulate to really see how the narrative is related to all the processes in between. But that second experiment is a beautiful example.
Yeah.
I didn't know I knew about the I forget the guy's name, the French guy who done these experiments claiming that there was that the intent appeared like 300 milliseconds before the doing it. And there's a great deal of dispute about that.
Yeah.
But it's amazing. And so that is, in my opinion, I don't know if you agree, but that is perhaps the ultimate illusion, is that we have free will.
Well, I would definitely agree with that. And so I just want to have actually one more comment and then some actual questions. We talk about AI and how spooky it can appear when we can practically carry on this dialogue, and we're surprised, how is this algorithm that's just essentially creating matrices of language, coming up with responses that sound just like a human would do it, even though sometimes maybe it's got wrong information, it's still responding in a way that's startling. And I think that really, for me, what it's revealing is not how close computers are coming to what humans are doing, but it's revealing a little bit more about what we actually already are, is we're just kind of running those same kind of scripts.
Yeah, but exactly, but yes and no. I mean, I give a little bit of physics in that chapter to point out that there's something different going on. At least the mechanism is different.
We're not doing it the same way.
Yeah, because if you took an electronic computer, and of course it's changed over the last decade, but claimed an electronic computer that had the same memory capacity and computational complexity, which is we're estimating things. They have these farms of computers, and it's a big problem with energy, right? Because it turns out that it was argued then that and it's probably now down by a factor of 1,000 compared to what the last thing I saw 10 years ago. But to have a computer with the same computational complexity and memory storage, et cetera, as the human brain would require something like 10 terawatts of power, about the same amount as humanity uses. All of humanity uses them. Our brain uses 20 watts. So there's some physical, there's something our brain is clearly not an electronic computer, or there's something different.
It's not.
And that's going to be, and a lot of people are, whether it's neural nets or a lot of people are trying to find what that computational method is. Maybe it will require, something else.
Yeah. Okay, so here's the questions. We go back to your magic tricks. You're illustrating two facts that deal with collapse of the wave function.
Yeah.
One for entanglement and one for basically the idea of the superposition.
Yeah.
So the question I have is, when you're doing the trick with the cards, we know that whatever card the person has taken from the deck is actually taken from the deck. But
how do you know that?
We don't know.
Yeah, we don't know. But I mean, you're making that assumption.
Well, I am. But
that it's
stick
a real
with me,
card.
We can see a card over there.
Yeah, well, I know, and you're making it up because that's the way the world works for us.
I'm saying
still
with the card trick.
Yeah.
It's a card trick.
Yeah.
There's an actual card.
Yeah, there is.
Right?
But maybe.
Now. So, if we go back, and we were talking about this the other night, to the beginnings of trying to make sense out of this quantum weirdness with Heisenberg and coming up with probability matrices to figure out where that electron was going to be, instead of trying to figure out how it got there, but what are the probabilities.
And all we can ever give is the probabilities.
Right. And then taking this mathematics of probability matrices and using instead Schrodinger's wave equation because it was simpler to work with.
For some people, anyway, go on, doesn't matter.
Wouldn't it then be a way of saying that what we're talking about with the wave function is a way of documenting our ignorance rather than the idea of a superposition?
No. No. In fact, that was a big question. So the question really is there a hidden reality? It's what Einstein always thought. The spooky action at a distance is just spooky because we are ignorant. Okay? I mean, it's like, look, you can say, I gave Jeff that card. We all know it has a real card. Okay? The fact that I didn't know what the card was till he told me. Of course, I knew what the card was. He told me, but the fact that in principle I didn't know what the card was, so he told me, is just a property of ignorance. It doesn't mean the world is weird. But in fact, what I was going to show you was a mathematical proof that the world is weird.
Okay.
That hidden variables don't work. It's not a property of ignorance. If I could give an experiment where I sent out randomly numbers to 3 people in this audience, and they were either zeros or ones, or -1 or +1. And the experiment, it's going to seem a little complicated, but it turns out every time, and you had a detector called A or B. And you don't know what that was detecting, okay? You checked A or B. You turned your switch to A, and it gave a number, +1 or -1. You turn your switch to B, + or -1. So I sent it out to everyone, and it turned out every time there was one person chose an A and two people chose B's, the answer was always +1. But since 2 people chose B's, B squared is always +1, right? So if ABB is always +1, if ABB is +1, or BAB is +1, or BBA is always +1, depending upon which 3 observers you have, that should tell you if I measure AAA, I'm always going to get +1. Because so the B squared is always 1. So, and it doesn't matter who's measuring what. It's not a property of who's measuring it or when they're measuring it. If I happen to have accidentally chosen AAA, I'm always going to get +1 because the A, if I just have one A, it always ends up being +1. Okay, it's not -1. I knew that the reason I didn't do it is I can see from your look that you don't understand what I'm saying. But anyway, so that's the sensible thing. But if I show you that it was actually a quantum mechanical experiment, the answer is always going to be -1. Even though if you measure 1 A and 2 B's, the answer is always +1. If you measure 3 A's, it's always -1. And that's impossible if before you make the measurement, the detectors had an actual value. It's impossible. It's not your ignorance of knowing it until you make the measurement. You can show that if those particles had the value, if A was really +1 before you made the measurements, or -1 before you made the measurements, the answer would be exactly different than if A was both +1 and -1 at the same time. And you can show with that experiment, you can do the experiment, and the answer is the world is weird. It's quantum mechanical. If you do the experiment, you get -1. I could write the mathematics down. It has to do with matrices and a little bit of more or less simple algebra. And I could show you quantum mechanically. I could tell you it was actually the configuration of sending three particles that I'd created in a very specific state, a quantum mechanical superposition of the particles all pointing up and all pointing down. I prepared that quantum mechanical superposition, and then I set 1 particle to each detector. And you can show the answer you'll get will depend on, basically, will be different than to assume that the particles were either pointing up or pointing down before you made the measurement. Because before you made the measurements, the particles were both pointing up and pointing down, and that's the only way you can get -1. So this hidden variable theory, the idea that Einstein had, that it's really a property of ignorance, and there's some hidden variable, if we really knew what it was, all this weirdness of quantum mechanics would go away. We can prove empirically that that's wrong, that the world really is, as far as we can tell, at a fundamental scale, quantum weird. It's not classical. Now, having said that, there's some pretty smart physicists, a friend of mine, Gerhard Tufte, who won the Nobel Prize, who still thinks at even a more fundamental level, quantum mechanics may be effective. Maybe what's it called when you get complexity? Emergent. It may be an emergent quantity of the world. Most people don't agree with him, but he's been a pretty smart guy. But still, every experiment we can perform, and a guy named John Bell gave an earlier version that's more complicated than the one I just gave. Every experiment we can perform tells us the world is not classical. The particles are doing both things before you measure it, and the answer you get would be dramatically different if they weren't. So different that you get +1 in one case and -1 in the other case. You can't get more different than that.
Okay, so one last piece to this then. I'll take your word for it right now. That's the way that it is.
I wouldn't take my word for it, but you can look it up.
Measurement in the past has been taken to mean conscious observation.
Well, not by physicists, by pseudoscientists, by people like Chopra or people who write The Secret or charlatans.
Okay, so when we're talking about the measurement problem, if we're not talking about consciously measuring something,
You don't need a conscious. When a particle, when all a measurement is, I mean, it's actually the science of understanding what measurements are is subtle. That's why these weird things seem, accepted but you don't need a person, okay? When a particle collides with another particle, it makes a measurement.
Okay.
You didn't need, in order for the processes in a supernova to create the elements, every atom in your body was created in a supernova, because the only thing that existed in the early universe was hydrogen, helium, and lithium. And except for lithium, which some of you may need, the rest of it, the rest, like carbon, nitrogen, oxygen, all those things are created in the cores of stars. Those nuclear reactions happened even though there was no one around to measure them, and we can predict and tell exactly how it happened and make the predictions and see what was happening. So consciousness, some people think consciousness is a central part of measurement. It isn't. You don't need a consciousness. You could just have a Geiger counter or a detector or just an elementary particle interacting. What a measurement is, I mean, it's somewhat, words never quite capture it, but approximately, a measurement is something that destroys quantum coherence. The quantum coherence is that correlation between your card and there, the thing that causes entanglement. But if going from here to Alpha Centauri, that card interacted with a lot of other stuff, there'd be no quantum coherence anymore, and whatever he saw would be completely unrelated to what I measure there. The weirdness of quantum mechanics is due to the fact that there's these coherence between states, and that is destroyed essentially by measurements. Not human measurements, but if they were interacting with gas particles on the way, there'd be nothing that would, and that's why we don't normally see quantum coherence, because the world is a complicated place, and there's particle interactions happening all the time. And that's why by the time it gets to a human scale of so many particles, we never see quantum coherence, and the world behaves classically, and that's why quantum mechanics seems so weird.
So another term I've heard for this is environmentally induced decoherence. So would that capture the idea that you're just simply, when something interacts with something else, that's causing the collapse?
Yeah, collapse is a misnomer, but it's causing decoherence.
Okay.
Yeah.
Very good. All right.
So are you making a distinction between observation and measurement?
And please repeat the question.
Am I making a distinction between observation and measurement? That's semantics. It's better to ask a philosopher that question. But the point is, yes and no. I mean, the only difference for me between an observation and a measurement is that a measurement, I can twist the dials and determine, and make things change. Observation, I can't. That's why astronomy is different than particle physics, right? Because I can see what happens out there, but I can't twist the dials in the stars. I can still try and use it and get information, but I have to accept the fact that I don't have control over the experiment I'm performing. So, but even observation doesn't require eyes, in principle. Okay, that's the problem of language. As I was just saying, T.S. Eliot, one of my favorite poems from the Four Quartets has to do with words, vanish, they become muddled, and it's a great line, but I don't remember poetry. And our language, and we were talking about this. I forget your name again. Matt and I were talking about this. He's an anthropologist and he's involved in linguistics. Our language, unfortunately, colors so much of the way we think about the world. But the language of nature is mathematics. So whenever I translate that language into words, it's always muddled. And you have to be very careful that the scientific usage is very different often than the colloquial usage. In fact, nothing versus something is an example of the scientific version versus the colloquial version are very, very different. But from what I said, they're both the same thing, as far as I'm concerned.
Well,
Schrodinger's cat.
Cat.
Yeah.
Okay. Is that observation? Is it measurement?
It's both. It's measurement. The point is, Schrodinger's cat. Okay. So you put a cat. I mean, the point is, an electron can be in many states at once. A cat usually isn't. But if you think about the cat as we're all quantum mechanical, but the problem is those quantum correlations wash out by the time you get to our scale. But if they didn't, you put a cat in, and it'd be a superposition in the box. It's a superposition of a live cat and a dead cat. Okay? And until the point is that you may, first of all, connect that box to a random quantum mechanical event like a nuclear fission, like a radioactive decay. And if the radioactive decay happened, then a gun would shoot and you'd kill the cat. Before it happened, the cat is in a superposition of live and dead states. Once you've shot the gun, it's not in a superposition anymore. But the idea is before you open the box, and you don't know if the gun went off, the cat is in a superposition of live and dead states. You make the measurement, you see which one it's in. And it's weird, but it doesn't work for cats, but it works for electrons. The electron, is in a superposition of states. You make the measurement and you always find it in one state. But that doesn't mean it was in that state before you made the measurement. That's the key point I make. The presumption is that it was in that state before you made the measurements. Quantum mechanics says it wasn't in that state.
No.
It was in all states, and the measurement, imposed that observational result, if you want. Okay.
Yeah, exactly. So the observation makes the determination.
Well, not always, but in that case, it turns out there are things called eigenstates, which are the same before or after the measurement. But generally, measurement interferes with the measurement determines the end result. And in fact, the colloquial version in quantum mechanics is that the measurement changes things. And anthropologists would say that when you go into a society, you got to make sure it's like Star Trek, the prime directive. When you go into a society, you change it by making measurements. And you got to be very careful if you're an anthropologist not to do those things, but it's hard. And yeah.
Any exposure.
Yeah.
We actually call that the Heisenberg effect.
You do call it? Yeah, to make anthropology sound like a science. It's really good.
We have a question over here.
I could resist. Okay. Yes?
You said that physics is predictions while religion is stories.
Yeah.
As a spectator of physics, not really a
Yeah.
physicist, it seems like it is a law of story, especially theoretical physics, which is making extrapolations from observations or from the real world. Is it really that physics is just predictions and is not a story at all?
Well, yes. In order to turn it into physics, we create stories. I'm paid to create stories as a theoretical physicist. Sometimes I explain experiments, so it's better than just creating a story. But even when I make a postdiction, in order to be physics, it has to make a prediction. So we think of the possibilities, but what becomes physics when we say that possibility would imply something about something you've never measured before, and you go out and measure that, and if you can measure it, I'll predict what the answer is. And if my prediction is wrong, then my story was wrong. And physicists learn to throw out those stories even if they love them. Now, some stories are so difficult to, like string theory, for example, now, is so complicated and difficult to imagine experiments that we can't do that yet. So it's still kind of just a story. But what turns it into science is when it makes a prediction. I mean, this is pauper falsification. But the idea is I can prove it wrong, then it's science. If I can't prove it wrong, it's not science. And that's why, I don't love to make fun of religion. It's fun to do, but it's still one of the things that is difficult is for a true believer. I'm never going to convince them. Forget religion. Let me use the example I was telling Cyan about earlier. Richard Feynman used to say, everything that happens to us is significant, but that's an illusion. Say you have a dream one night that your friend is going to break their arm. You wake up, your friend calls you, said, I broke my leg. So you say, cosmic. Okay? You forget that 1,000 nights you had 1,000 ridiculous dreams that never happened. Okay? But you remember the one that happened. Okay? Now, if I tell you that it was just a coincidence, it's going to be hard for you to believe. Let me give you a better example. Actually, Carl Sagan used this in his book, Demon Haunted World, one of my favorite examples.
It's a great book.
Is the miracle at Lourdes. If you go to Lourdes and you go in the water of Lourdes, you're supposed to be cured. The Madonna or the Virgin Mary will create some miracle and you could be cured. People flock there. 120 million people have gone over there since this person claimed to see an image of the Virgin Mary there. And the Catholic Church keeps very careful records of the number of miracles. The people who were cured. And so, over those 120 million people, like say 20 of them have had their cancer go away. Okay? No one's ever regenerated an arm or a leg. Okay? We say, okay. But it turns out, in the real world, cancer goes into remission spontaneously for some people. If you actually calculate the probabilities, you have a less of a chance of being cured if you go to Lourdes. Among the background population, more people have spontaneous remission than the 20 over 120 million. So there's less of a chance that you can be cured if you go to Lourdes. But if you go to Lourdes and your cancer goes into remission, there's no way in hell I'm going to convince you it wasn't a miracle. Right? And that's the point. And so, because I can't falsify it, I can't prove to you, I can tell you that, but you'll believe, no matter what, that random thing was significant. And that's what we have to overcome. We have to, we're all like Fox Mulder in the X-Files. We want to believe. And we have to, and scientists have to constantly tell themselves, as Feynman said, the easiest person to fool is yourself. Because everything that happens to you maintains a significance that may not be significant. So whenever and I've seen it happen in experiment, Feynman was great. I've seen experimentalists who are so deluded because they're doing an experiment, they see something weird. And I've discovered something. But statistics tell you weird things happen all the time. They're just random, and you have to recognize that if you're looking for weird things, you're going to find them. But that's not the right way to do it. So look at the thing, not look. Do a blind experiment. Don't look for the weird things and you'll find out they don't happen. So experimentalists many times delude themselves because, boy, when you see something weird, it really has significance. So we have to try and train ourselves to be skeptical of the things that appear to be significant to us. And science gives us a good practice, but scientists, it's a secret, scientists are people. And they all suffer from the same kind of natural delusions as the rest of humanity. Is that a good name? And we still have some time left. But
Yeah, we've got a question in the back.
Okay.
So how, in your world, use AI?
How do I use AI? I don't use AI. I played with ChatGPT once when I wrote an article showing that it was biased and woke. I asked it about gender. This was early days, and it refused to give me a right answer. And the problem is, and people know that, but AI is trained. So right now, the results it gives you depend on what it's trained on. And you can make it biased, you can make it woke, you can make it do all these things. And those are changing. But AI is used tremendously in experimental physics. Because AI, as I told you, is really good pattern matching. It sifts a lot of data and looks for, and so it's being used in protein folding to look at all the different. It's computationally almost impossible if you have all these proteins, and even if you know the electromagnetic interactions, to know how it's going to fold. But if you look at train up AI in 1 billion different proteins, it'll be trained kind of guess how you put a bunch of things together, how it's going to fold, and it does pretty well. And then when it's right, if you train it on that, it does even better the next time and the next time. And galaxy correlations. So people are using machines to analyze data very effectively, and it's being used in the physics world a lot. So it's basically guessing the right answer to things, and that's going to continue to improve. And so AI will definitely be useful, and it'll put a lot of people out of work. Okay, it's obvious. It's obvious that at some point AI will be a much better diagnostician than a doctor, right? The problem is if you go to a medical facility and AI says, okay, let me analyze your systems, do X, and you say why? I don't know. It just works, right? That's what a neural net will basically do, because it won't tell you how. It'll just tell you it works. Will you be happy enough to do that? But of course the problem is that's what happens in medicine right now anyway. A lot of the time the doctor will pretend they know the answer, but they'll just have done what works. But anyway, AI is going to display. It's the opposite. Like science fiction is always wrong. I'm sorry. It misses all the real things. When I was a kid, by now I was supposed to be in flying cars and all the rest, but it didn't tell me the internet was going to happen, right? And it misses the big stuff. And I remember when people talk about AI, they talk about robots, and robots will be, the Jetsons. They'll be doing the dishes, and they'll be, mowing the lawn. Actually, the menial jobs probably a lot harder to misplace than the more professional ones, lawyers, doctors, all of those things. That AI will probably displace them a lot better. Now, the world would be better if all the lawyers were displaced. I'm not sure if about the doctors. Yeah?
Yeah, so yesterday I was asking you about Star Trek and the teleportation.
Mm-hmm.
And you said, and I said, well, what happens to consciousness?
Mm-hmm.
Is it possible to teleport? And you said maybe for animals, but not for humans?
No, I didn't say for animals. I said for electrons. The point is, that I wrote about in my book, The Physics of Star Trek. Okay, the question was teleportation in Star Trek. Is it possible? Can you and and that's what got me into writing the book, because I take planes and I'd rather not. It'd be great to teleport, but and is it possible? And I started to think about that. Now, it's not possible for humans, I would argue, and I'm right. But it would be but it is for electron. We have things called quantum teleportation. It looks good and it gets a lot of attention because it has that word teleportation. And quantum teleportation says, using this entanglement, if I prepare particles in a very particular state, I can recreate. If I have a particle here, I can recreate the state of this particle over there instantaneously by doing an experiment. Instantaneously, and it's over on the other side of the universe, instantaneously, if they're entangled. But we're not quantum beings in that sense, right? We're not. If we were, quantum mechanics wouldn't be so weird. And so we're a very complicated set of systems that are interacting a lot. So here's what I said when I thought about teleportation. First thing, Star Trek tells you how to teleport. Like they tell you, first I vaporize you and turn you into atoms. And then I take the matter stream and I take it from there, then I just put the atoms together again. There's a problem with that. If I want to vaporize you at the atomic level, I have to heat you up to about 100 billion degrees, okay? It's problematic. I release the energy of about 100 megaton nuclear weapon explosion. So as engineers say, it's not environmentally friendly, okay? Okay, so that's a problem, but that's not how I would make a transporter, okay? What I would do, I would scan you and take all the information that makes you up as a human being, okay? Then I transport that information over there. Then I take some atoms I already have over here, put them together with that information, make another copy of you. But that's not a transporter because you're still over there. Well, it's simple. I vaporize you, and now you're only over here, okay? The problem is the Heisenberg uncertainty principle. In order to scan you and know all the information that makes you up as a human being, I have to know at the atomic level what the configuration is of every atom in your body. But the problem is, when I do that, I change things. Right? I can't know for example, I can't know, not just a matter of the quality of my experiment, I cannot know where every atom is in your body and what it's doing at the same time. Exactly. I can know them pretty well, but there's always some uncertainty. Very small uncertainty given by Planck's constant. Okay? So I could make a really good approximation of you over there, but I'm not sure you want to be transported. Okay? And so the problem is, because of that, I can't transport you as a human being. It turns out the reason I can transport an electron is I can do the experiment without making a measurement because of quantum entanglement. Okay? But because you're not a coherent quantum object, I can't entangle you with the atoms over there effectively. And so that's why I can never make a transporter that will transport you. Okay? Now, I've actually had a great deal of fun with a friend of mine who's a really brilliant geneticist, saying maybe I don't have to recreate you at the atomic level. You know, you can take these certain kind of worms and you can train them, and then you cut them up in little pieces, and then they regenerate themselves, and they'll remember, right? So maybe what really makes you up as a human being isn't at the atomic level, and it really isn't quantum mechanical, and maybe I can recreate you with the memories you have, just with a coarse graining of your body, and then I could have some atoms over here. It'd still be practically impossible for me to put the atoms together in the right form. That would take more energy than humanity uses. But as a question of principle, maybe that's possible. But anyway.
Well, the other thing I think would be an interesting question for that is, if you were able to, let's say, take apart and put back together, even if it wasn't in a different location, there's something about life that is a process, that it's not like you can just restart it.
Well, I mean, but you restart, you're Dr. Frankenstein. You give it the energies, you give it, put electric things on. But, in fact, it wasn't you, but it was someone else said, what about a soul? And I wrote in my book, I said, it'd be a great way to prove there's no such thing as a soul. I wish we could do teleportation. Because, what happens to the soul when I vaporize you and just take your atoms? And if you're exactly the same person over there, then it suggests all you are is a mechanical compilation of a bunch of atoms, which is all you really are. And it'd be a great way to prove there's no such thing as a soul, but unfortunately can't do it. Yeah?
Yeah, you made the statement that consciousness is the ultimate illusion. So we're all sitting here in this room. I think most of us are awake.
Uh-huh.
We're listening to you.
Uh-huh.
So is this all an illusion? I mean, what?
Well, no, you see, that's what I want to point out. There's illusions and there's illusions. When I say it's illusion, you get the sense that there's no reality. There is a reality.
Yeah.
The reality is different at some level, and it depends on the circumstances than we might perceive it to be. In the case of quantum mechanics or time or the mass of particles, at a fundamental level, it's dramatically different.
Right.
But I'm not suggesting that
We're living in a classical world.
yeah, but I'm not suggesting that all of reality is subjective. In a sense, it is, but I don't mean it in the sense that some people think when they mean it, that basically you're only there because I think you're there. I actually, I don't use the word believe. It's highly likely that you're there, whether I think you're there or I'm not. And so it's not. It is true that I'm putting together this picture, but I don't think that really means that I'm recreating a reality that isn't there. Nor do I think that you're experiencing something very different than I experience. And I do that. I have empirical kind of evidence about that because we can relate as human beings. And I tend to think that when I saw the eclipse, other people saw the eclipse near me. So there's a lot of empirical evidence that leads me to that suspicion that it's highly likely that there is an objective reality that we agree upon in almost all cases. But I'm also willing to recognize that because it's filtered through our brain, there's some aspects of the underlying reality that we may disagree upon because of our perception. So that's the difference between, I'm not saying there's no objective world, which is really the bugaboo of the New Age mystics, okay? And that's not what science is saying. There is an objective reality, but the reality is stranger than you ever imagined. Okay.
I think we've got time for one more question if somebody's got one.
You don't have to, though. If you don't ask it, we'll have more time for coffee, yeah? or lunch, actually.
Do you think that AI will finally provide some mathematical method to finally solve the three-body problem?
Who knows? And maybe a quantum computer will be able to give you. I'm suspicious, no, but I suspect that AI will develop new mathematics and give us enlighten us. I expect it could enlighten us about lots of mathematical problems that we can't answer. That's the fun. And as I say, as a physicist, I would love to know what physical questions an AI found interesting, much less learn from its answers. But who knows? The answer is I don't know, and that's what makes it exciting. The future is terrifying and exciting, and that's what makes life worth living.
All right. Well, thank you again very much.